Okay, welcome to part 2 of 6.3. Now we're going to be looking at solving exponential equations, which has a special property called one-to-one bases. So what we have here is that if you have two exponential expressions that are equal to each other and the bases are the same, then their exponents have to be the same. So in all of these problems here, we're going to work to get the base to be the same value on both sides of the equal sign. So our first example, as you can see, both bases are already base 5. So that's a one-to-one base property. You can cancel the bases out, set the exponents equal to each other, and just go ahead and solve for x. So add the 4 over to the right, subtract the x from the 3x, you'll get 2x is equal to 4. We'll divide by 2 and x is equal to 2. My second example here, we have base 2 to the 2x minus 7, but this is equal to 8. So that means we need to rewrite 8 as a base 2. Well, we know that 8 can break down the 2 times 2 times 2, so 8 is the same as saying 2 to the third power. So now we're a one-to-one base relationship. Cancel the base 2's, set the exponents equal to each other, and we'll solve for x. So add over the 7, 2x equals 10, divide by 2, x is equal to 5. My next example, it's a little bit different here. So here's base 27 to the x minus 2 power, but okay, we can't turn the base 9 into a 27. So what we're going to probably have to do here is try to break the 27 down to maybe match the 9, but 27 breaks down to 9 times 3. 3 is actually smaller, so I think we got to break both bases down to a 3. So 27 is 3 times 3 times 3, 9 is 3 times 3. So I'm going to rewrite this as 3 to the third power for 27, raised to the x minus 2. Your 9 becomes 3 squared. But we don't have a one-to-one base relationship, so what we're going to do is we have a power raised to a power. So we need to multiply these two powers together. So that's going to be 3. This 3 gets multiplied to the x and the minus 2, just like the distributive property. We have 3x minus 6. Now it's a one-to-one base relationship. It wasn't up here because this base was 3 to the third power, so we had to simplify the powers. Cancel your 3's. 3x minus 6 is equal to 2. Add over the 6 makes it 8. Divide over the 3. X is equal to 8 thirds. And again, if you want to double check, you could store 8 thirds in for x. Type in 27 raised to the x minus 2 power, and it should come back as a 9. Over here, we have base 4, and we have 1 over 32. Well, 32 is a base 2 number. 4 is a base 2 number. So 32 is 2 to the 5th. I think we saw that earlier. So here we'll have 2 squared to the x plus 1 equals 1 over 2 to the 5th. Well, just like we did in the last problem, we'll have to multiply those powers. But we're also going to have to use the negative exponent rule to move base 2 from the denominator up into the numerator. So we'll change that 5 to a negative 5. So 2x plus 2, multiply the 2 to the x plus 1 binomial. Now we're one-to-one, cancel those 2's. 2x plus 2 equals negative 5, solve for x. Subtract over the 2, divide over the 2. X is equal to negative 7 halves. And our last example, kind of tricky here. 4 to the x times 2 to the x squared equals 8. Everybody needs to be changed to base 2. So 4, 2 squared to the x, times 2 to the x squared. No change there. And 8 we saw from earlier is 2 to the third. But this is 2 base 2's to 1 base 2. So we're going to have to multiply these like bases. And if you know, when you multiply like bases, you have to add the exponents. So 2 times x, that's going to be 2x. Multiply like bases is going to be 2 to the x squared plus 2x. So I just wrote that in descending order. Now it's a 1 base 2 to 1 base 2. Cancel your base 2's. X squared plus 2x equals 3. I've created a quadratic equation which has to be set equal to 0. So I subtract over the 3. We factor that. X plus 3x minus 1. Solve for x. X equals negative 3. And x is equal to 1. Okay. Next, we have some examples where we're going to work with our exponential base b to the x, but there's going to be some kind of a being multiplied to it. And you're going to be given 2 points, and you have to write the exponential function. All right? So here, good point is because you have an x coordinate of 0. This is your common point. Well, we're not at 0, 1. That means this 400 has to be your a value. That's the value that got multiplied to your 1. So 400 goes in for y. You put 0 in for x. B to the 0, remember that's a 1. So a is equal to 400. We'll take that 400, substitute it in for a of our original equation. And then we're going to plug in a point. I'm going to work with the second point. Can't use the first point. I've already done that here. But now with the a being 400, we're going to put in x of 3, y of 50, and then we'll just solve for b. So I'll divide over the 400. That gives me 1/8 is equal to b to the third power. Take the cube root of both sides. B is equal to 1/2. Now I found my a is 400, my b is 1/2. I can write my function f of x is equal to 400 times 1/2 to the x power. My next example, now we have a point. There's no zeros for the x. So when there's no 0 for the x, what we're going to do is you have to subtract your x coordinates. All right? So take your second x minus your first x. That's a 5. That 5 is the power on your base. So what's happening here is first y coordinate, 0.375, multiplied to b to the 5th has to equal 12, and that's how you create an equation where you can solve for b. So I'll divide over the 0.375 into the 12. That's going to give me 32. B to the 5th equals 32. So, all right, that's 2 to the 5th. Saw that earlier. So 1-to-1 base relationship here. Powers are both 5. So B has to be 2. So now that I have B, I still have to figure out what's that value for A. So we're going to plug in 2 for the base and plug in a point. I'm going to go with the second point because I don't want to work with negative x and I don't want to work with decimals. So I'm going to go with 212. So 12 is my y coordinate equals A times base 2 raised to the power of 2 because that's my x. 2 squared is 4. So 4 equals 12. A is equal to 3. My function f of x is A is 3 times base 2 to the x power. Another thing I encourage you to do is double check with your calculator. I stored in this function into y1, 400 times 1/2 to the x. Plugged in this function for y2, 3 times parentheses 2 to the x power. And then don't graph it, but hit the table, second graph. It creates the table for you. So 0, 400, 350 for y1. There's 0, 400, 3 and 50. Those points match up with my function. Over here, our x's were negative 3 and 2 for our second function. Negative 3, there's the 0.375, 2 and 12. That's our second point. Now, another thing we're going to have to do is we're going to have to find the exponential function given a graph. So Predominantly, you are looking for your common point with relationship to your horizontal asymptote. When that's 1 unit away, that's my common point 0, 1. Then remember we talked about those 3 points. To the right of 0, 1 was 1 comma the base. So if we go 1 to the right, we count up 1, 2, 3, 4. My base is 4. Again, you're counting from the horizontal asymptote. Not always the x-axis, not from the common point, but from the horizontal asymptote. So right now, this is f of x is equal to 4 to the x power. So what we're going to do is they're going to move a graph around, and you still have to figure out what is the function. So for example, here they've really mixed things around. Now, there's 2 ways to approach this. Some people will say, find the location of your common point. Again, that's 1 unit away from the horizontal asymptote. Go 1 to the right, and now count 1 from the horizontal asymptote, 1, 2, 3, 4. And say, okay, base is 4. This is my beginning function. Now, some people, some teachers, some authors will talk about moving this graph back up to the top. Okay? Well, if you flip the common point over the horizontal asymptote, it goes right there. Well, when you flip over the horizontal asymptote, that's a negative now being multiplied to your base. Now, to get up to our normal location of 0, 1, we're going 2 to the right and up 3. But again, that's really not our transformations. You would have to take the opposite of those. So remember, for your transformation rule, say you start here and you want to end up here. So I really need to go to the left 2 and down 3. So left 2 means I need to make that change up here by my x. So x equals a negative 2. All right, move the x back over, x plus 2. And down 3, that's going to be subtracted at the end. And this would be my function. I'm not a fan of doing it this way because of the fact you got to remember to change those directions. So I prefer to look at it this way. I still agree getting to 4 to the x. I agree with that part there. But what I do is I like to just put my original 4 to the x up here. Here's my common point. Start there. Now, I got to look at this and say, oh yeah, I got to flip this over the x-axis. That's my negative 4x. Then I got to go left 2. Okay, that's going to be my x plus 2. And then down 3 to get to this location of the common point. So that's my minus 3. That's the way I like to look at it. Start with the basic function like we did with the graphs in the previous video. And then go ahead and do your transformation rules to get there. And that's the last of 6.3.